In this class activity, I asked the students to estimate the width of my classroom from front wall to back wall in meters, not by standing up measuring. They had to sit in their seat and just look and kind of guess what they thought. So here were their estimated widths: 8, 6.5, 6.75, 7.2, and so forth. We had just a small class doing this. So I made a dot plot of their guesses, and then we also used the calculator to do some one variable statistics, and we got these values. So the mean guess was 7.9, standard deviation 1.35, the lowest guess was 6.5, the highest was 10.25, the median guess was 7.2, and so forth. And you can see that we have kind of a little cluster between 6.5 and 7, and then a few higher guesses that are sort of skewed to the right over there. Now then I revealed to them that the true width was 8.55 meters. So the second thing we did then is using our calculator, and I'll show you this on the calculator, we did a really efficient way of going back to speaking of efficient, I need to get back to my document. We entered the first group as called estimate in meters, and so I entered all those values, and that's where I got the one variable stats and made the dot plot and so forth. Then I made a second list called error, and in this box below I can set a formula, and basically here in this box I type in equal, I grab this, I go to the variable list here. That's not working well. I'm actually not typing it. So let me just show you, kind of go through what I did. Equals, then I go to estimate M minus 8.55. And it gives me all of the errors. Then I was able to make a dot plot and do one variable statistics on all of the errors. So this tells me how many meters above and below the true meter that students guessed. So when we looked at all that information, scroll down a little bit here. So notice now that we have the error and estimated widths. The dot plot looks very much the same, except the scale is just shifted. So instead of being centered, having the mean of about 7.9, now the mean is 7.9 minus 8.5. So the mean now is just it's close to 0, but a little bit on the negative side. So we see that these 3 values guessed too high, and these 5 values guessed too low, because 0 represents the correct guess in this case. Now I want you to notice what happens to all of the different statistics when we add or subtract a number. So when we added 8.55, notice the mean changed, the standard deviation did not change. The minimum, the Q1, the median, the Q3, and maximum all changed. They all were 8.55 less than they were before. But notice the IQR and the range don't change, because the IQR is just the difference between Q3 and Q1, and in this case both of them shifted down 8.55 units, so the difference between them is the same. Same thing with the range, which is the maximum minus the minimum. They all everything shifted to the right, or to the left, 8.55, so the difference between them is still the same. So that's why the graph looks very similar here. The shape, notice, is unaffected, but only certain statistical measures are changed. Then in the third step, what I had everybody do is change meters to feet, because most Americans think in feet better, probably could have possibly estimated better in feet. So we use the conversion that 1 meter equals 3.28 feet, and once again on my calculator what I did here is equals estimate in meters times 3.28, and it automatically populates the list in feet. And I did another a dot plot. And notice here our mean, if we compare all of our values, before the standard deviation, the IQR, and the range didn't change. Now notice that all of those values are 3.28 times what they were before. So if we took standard deviation times 3.28, IQR and range times 3.28, and then all of the other values are 3.28 bigger than their original values, not the one before. So mean was 7.9, now multiply that by 3.28, we get 25.98. So when I made Now, when I showed the dot plot, obviously this dot plot is more spread out than this one. This only goes from -2 to +2. This goes from 21 to 34, so it is not the same amount of spread. This one was from about 6.5 to about, let's see, 9, I don't know, 6.5 to a little over 9.5, so close to 10. So this is about a spread of 4. Actually, you can see the range is 3.75 for both of those. Now the range is much bigger. The range is 12 here. So it is more spread out. I went ahead and made a comparative box plot to show you exactly what happens when we do different transformations. Here's the original guesses in meters. Here is what happens when we subtracted the true mean of 8.55 meters from every value and got the errors. Notice the box plots are exactly the same shape and size, they're just shifted to the left, 8.55. So instead of being right here between 5 and 10, they're between -2 and 2. So measures of position, anything that measures a position, the maximum point, Q1, median, Q3, the minimum point, the median and the mean, all of those measure a specific spot on the graph. All of those change. So those are called measures of position. The measures of spread, things that measure how wide the graph is, do not change because you're subtracting two values that have both shifted, so the amount in between is still the same. But when we multiply or divide now, measurements of position and spread are both affected by multiplication and division. So we see that not only did the graph shift over, it also stretched, in this case, by a factor of 3.28. So this is 3.28 times wider than it was before. All this did was it shifted left 8.55 units, because that's what we subtracted. What doesn't change at all when the scale changes? If we look back at the 3 dot plots, their shape is exactly the same. They're still all unimodal, skewed to the right with some outliers, and that doesn't change at all. And you can see that in the box plot, that the actual shape of the box plot, where the median is located within the box, the length of the little whiskers, those don't change. It's just stretched, and it's a little different in that regard.